All right, so this is NLP for related languages, just lots of work, random stuff that I've done throughout the years. And these are lots of people who helped with all of this. This is not just me. This is a huge collaborative effort, or really a collection of collaborative efforts. So today in the world, there are about 7,000 languages. And we have high resource languages that have a lot of data. Oh, can we let me see if I can. Okay. Is it okay if I minimize that little window thing, Sabrina? There we go. Is that okay? Okay, I think that'll be fine. Yeah, so we have high resource languages like German, Spanish, and Mandarin that have lots of data. Low resource languages like Haitian, Swahili, Telugu. We have very low resource languages like Guarani, Luo, and Fante, and or Fanti, and we have endangered languages as well, like Louisiana Creole and Central Pueblo Nahuatl. So these high resource languages, that comprises about 12 to 50 languages, depending how you count them, and the rest fit into these other three categories. So this is a picture from the Endangered Languages Project. These are all endangered languages to varying degrees of endangered. So these are all just in that very bottom category, let alone even the other three. And as you can see, there's a lot of languages here. Kind of the point of this is that the majority of the world's languages are low resource. So here's some lingo. It's not really Duolingo. I just thought we'd throw that on there just to, send some props to our friends over in Pittsburgh. But I'll use LRL to mean low resource language and HLT to mean human language technology. So LRL communities need HLT. Let's see. Yep, time to buckle up because I'm going to pontificate about why this is true for the next 8 slides. So a lot of languages in the world are what we call minority languages, where they are not the majority language spoken in the area where they're spoken. And so these are situations and people who often need translation resources just to communicate with other people and navigate social opportunities in the places where they live. This is also the case for migrants or people who live in areas where their language isn't commonly spoken. So this is just an illustration of the Haitian diaspora and the Indian diaspora. Natural disaster relief. Often, for instance, okay, so just for example, the Haiti earthquake in 2010, it caused a lot of devastation and international workers went to help, but because the Haitian language is low resource, they had difficulty communicating. And so translation tools were needed. And this is an active field of study in other places as well. Singapore, Kathleen McEwen has done multiple presentations on this topic. Endangered language documentation is another need. So I talked about Louisiana Creole. Yoloshoshit Mixtec is a language that researchers at CMU have studied how to help preserve via speech technologies. And I guess this is just a plug for some work I did with my colleagues there as well, where we introduced this new data set for all these different endangered languages and a methodology for how to assist linguists who document these languages via speech recognition and linguistic segmentation. These languages often have a history of marginalization. So on the right, we have an article by Michel de Graaf about the marginalization of the Haiti language socially. We also see minority languages in places like China that often aren't supported. And this is a tweet from me about how ChatGPT is bad at African languages, often due to lack of support. There can be limited LRL literacy. So often LRL speakers, they might be literate in a language, but not their native language, or they might not be literate at all. And so these are situations where people really are in dire need of speech technologies because they can't actually interact with technology via text. This map just shows illiteracy rates throughout the world, kind of highlighting some areas where this is important. And then there are also strong oral traditions, often in LRL communities like this Quechua woman telling stories that are pertinent to her culture. It's also important to do HLT for LRLs just to study diversity of HLT capabilities. We have a lot of technologies that work well for a small group of languages, but that might not translate to the greater community of languages. And it's also good to include LRL communities in HLT development. That way we can sort of build HLT and opportunities. Data that we face nowadays is that for neural machine learning, we need big data, lots of data to train these models and get high performance. And these are things that aren't available for LRLs. Often we need annotated data, like by text with translations or audio with transcripts. Often we also just need large amounts of data and segmented corpora or speech corpora. And these are things that are scarce for a lot of these languages. This shows the long tail of data. We're approximating resourcedness by the number of Wikipedia articles, but it just shows that the vast majority of languages don't have very much data online at all. And this is sort of the great irony of multilingual NLP, which is that those with the greatest need often have the least access. In 2023, as we know, LLMs became popular among non-researchers, and they have the ability to support more languages out of the box, potentially without specified fine-tuning data sets. And so, here's the potential through LLMs just trained on lots of web text that we might not need some of these annotated resources. Many languages have no benchmarks, though, to verify if LLMs actually work in that language. And this is something that we need to verify experimentally, in part because LLM providers are not incentivized to publicize their model's shortcomings. So these are things that need to be approached from sort of an academic standpoint a lot of the time. We have seen an expansion on existing LLM MT evaluations. This is work that I did last year with some CMU colleagues, but essentially, when ChatGPT became really popular, people were evaluating how well it does machine translation, but mostly focusing on a small number of languages. And so we expanded this significantly to 200 languages supported by the Flores 200 benchmark. And essentially, one of our main takeaways was that traditional MT generally beats LLMs for these low resource languages, the languages that aren't getting as much support. And so we found that NLP and Google were typically doing better on average. And that GPT-4 was better than ChatGPT, not super surprising. And Google was the best on 100 out of the 115 languages that it supported at the time. We had an average of 12 CAREF points increase this is NLP beat ChatGPT on 84% of the languages. This is significant because NLP actually supported all of those languages, whereas Google Translate only supported a subset of them. And it did better by an average of 12 CAREF points. Some interesting correlations we found are that it actually had a lot to do with the resource level of the language, how well ChatGPT did or NLP. So 5-shot ChatGPT did better than NLP for 47% of HRLs, high resource languages, but only on 6% of the LRLs. And when we fit a decision tree trying to predict the percentage improvement that NLP, so essentially we compared both 0-shot and 5-shot ChatGPT. I'm just pointing because the 5-shot was better. I'm just pointing at the NLP was better than the better of the two ChatGPT settings. Yeah, sorry. So that means there were 5 in-context examples, source translation, and so on. And that helps ChatGPT to do a bit better. This study actually found that the improvements were somewhat marginal, and that still NLP typically did better, particularly when focusing on the low resource languages. As you can see with the high resource languages, it's kind of half and half, which one is better. When we fit a decision tree regressor to predict the amount of improvement that NLP had over ChatGPT, and we found that I guess really what we were predicting was the inverse, the amount of improvement of ChatGPT, but we found that the worst group of languages for ChatGPT were specifically Niger-Congo languages with fewer than 3.7 thousand Wikipedia pages. And the sort of first delimiting feature, as well as the most important feature in a random forest analysis, was the number of Wikipedia pages. This was the most important feature in determining how well NLP did compared to ChatGPT, with ChatGPT doing worse on the lower resource languages. And we found particularly,
what the metric is when you said doing worse?
Yeah, so essentially this is CAREF score. And when I say doing worse, I mean so basically we measured the percentage improvement of ChatGPT over NLP, which was typically negative because NLP was usually better. And CAREF score, character F score, this is just a machine translation metric. It's sort of similar to Blue score, but it's often used for low resource language evaluation just because it's often considered a little bit better than Blue score.
Okay,
So,
and sorry, you may have said this, but the task is to translate into these languages?
we were translating into the languages because we were using the Flores benchmark, where the English sentences themselves were actually taken from Wikipedia and wiki resources that ChatGPT has probably seen. So we didn't feel we could fairly evaluate into English translation with that benchmark. We found that it was particularly bad at African languages. So when we group things by language family, as we did here, the two worst languages for ChatGPT compared to NLP or the two worst language families, I should say, were the two exclusively African language families. And then we saw a similar trend with the scripts. So this is like Latin, Arabic, whatever script. The two exclusively African scripts were Tifinagh and Ge'ez script, and they were, again, the two worst for ChatGPT. So we found that ChatGPT is, worse at these groups of languages, and it's also costly, particularly GPT-4. This is the estimated cost of just running inference on one of the Flores test sets. So as you see for NLP, it would be about 9 cents. ChatGPT even about 35 cents, but GPT-4 would cost about $26. And this is significant because a lot of low resource language speakers might have fewer economic resources. Yeah, sorry, this is a lot of information, but basically when we divided the scores by the estimated cost, this purple bar in the top charts is GPT-4, and you can see that it dropped like crazy in the bottom charts when we divided by the cost. And NLP we found with sort of the red bar being highest in these bottom charts. Okay, so this basically our promising options are back to, since the LLMs often aren't as good, or at least these star GPT LLMs aren't as good for low resource languages in MT, but other works have corroborated this conclusion. We could improve the LLMs for the low resource languages, or we could go back to trying to get those annotated and large data resources that we wanted before. Both of these are expensive though. And so this is some of essentially, it looks like HLT might be out of reach for many LRL communities. But wait, languages are related, right? This just shows some like trees of languages and how they've evolved from each other and their relationships. So maybe we could use a cross-lingual transfer. So this is a language called Haitian Creole. It's closely related to French. What if we used all of the data and resources available for French and we're able to transfer some of that knowledge to Haitian Creole? So one way to do this is through multilingual MT. There are actually focusing specifically on machine translation, there are lots of cross-lingual transfer methods that have been tried in the past. So you can train a model on multilingual data all at once. You can, pre-train on a high resource language and then fine-tune on a low resource language. And this has shown promising results not only in MT, but in speech recognition, where models like XLSR that were trained on a group of high resource languages, they do much better even for unrelated low resource languages. Languages can sometimes be kind of grouped, or I should say a lot of low resource languages are related to a high resource language. So in the blue, we see French-related Creole languages that are all closely related to French. And on the right, these are English-related Creole languages that likewise have a relationship with English. Here are some Arabic language varieties that are all closely related to Modern Standard Arabic, where the dialectal varieties are low resource, Modern Standard Arabic is high resource. And then over here on the right, we have Sinitic languages that have linguistic relationships with Mandarin, which is also high resource, while the others are low resource. But let's focus on Haitian and French. So roughly 90% of Haitian lexemes are of French origin, and they have similar pronunciations. So we have parler, parler, comprendre, comprenne, fromage, fromage, and then we have some words that are just not related at all, like avoir and gain. So when we do cross-lingual MT, what we're focusing on here is we combine the Haitian data with data from a high resource language and we train, and then at testing time, we just test on the Haitian translation. And here we found that, yes, combining French with Haitian did improve the results from 43, or I guess 44 to 46 blue. But Haitian plus Spanish actually did better. And so the question was, why is Spanish seeming to help even more than French when Haitian and French have these well-documented linguistic relationships with each other? So that was kind of something that stumped us. We're not the only ones to reach conclusions like this. Heather Lent, a prominent Creole NLP researcher, said, quote, ordinary transfer methods do not enable ancestor to Creole transfer. So let's explore what this means a little bit. How are French and Haitian related? They have high phonological and lexical similarity, but they have low syntactic and orthographic similarity. When I say syntactic here, I sometimes mean morphosyntactic, but basically how similar are the grammars of the languages. And these relationships not only describe Haitian and French, but also pairs of other languages like Maltese and Arabic, Lao and Thai, Jamaican and English. So it's an important sort of dynamic to explore. Haitian is actually morphosyntactically related to African languages. And so essentially, yeah, okay. I'm just explaining this. So conventional MT systems, okay, so they do have high phonological relationships, Haitian and French, but conventional MT systems do not process phonological information. So using that for MT transfer is kind of out right now. They have high lexical similarities, but the lexical borrowings are obfuscated by orthographic differences. So if we see comprendre and comprenne, these are spelled completely differently, and they're not going to have any token overlap. And the sentence structure is unrelated between French and Haitian. So essentially, if they're not benefiting from the phonological or lexical information, then we're essentially not really getting anything from their relatedness together. So therefore, the benefit of relatedness is not actually even taken advantage of. So now let's talk about these dimensions of linguistic relatedness. Because clearly we can't just say, oh, these two languages are related, therefore they will help each other. It actually depends how they're related to each other. So we'll explore phonological, phylogenetic, structural, and acoustic relationships. Here's just a little more lingo. I'm kind of preaching to a group that already knows these acronyms, but TTS means text to speech. Okay, so cross-lingual transfer for MT, I already went over these first two. We also have parent-to-child fine-tuning and embedding sharing that can help in these scenarios. And this is basically in these experiments, we focus on bilingual source training, where we combine, I sort of mentioned this before, but we combine the high resource language with the low resource language at training time. Okay, so one way that we can overcome the differences between Haitian and French, or the orthographic and syntactic differences, is by using a rule-based engine. So when I was in my undergrad, I made this just based on my own knowledge of Haitian and French. And it's like, I think 90 different rules about just transforming a French sentence to Haitian. It's basically a rule-based MT system. And it actually works pretty well. So essentially we have a syntactic transform where the word order is changed and an orthographic transform. You can see the original French, if you go from there to the orthographic transform, the order of the words is still all the same, just the spelling changes. With the syntactic transform, you see the order of the words change, but the spelling is the same. We can also apply both, which gets us something close to what the Haitian translation is. And to my eyes, the outputs look pretty good a lot of the time. But if you evaluate this with blue, it's actually really bad. So there are still a lot of errors. To take advantage of the phonological similarities, we actually made a shared embedding space for Haitian and French. And we did this by taking the text using a G to P system, which puts them in the International Phonetic Alphabet. So then, words like comprendre and comprenne will actually be spelled similarly. And then we used a pan-font feature vectors, which essentially convert those International Phonetic Alphabet characters into vectors, sum them together. And so the benefit of this is that words with close pronunciation will have a close initialized embedding, like unité in Haitian and unité in French. Okay, we also ran some of these experiments for Jamaican and English. In this case, I don't speak Jamaican. I couldn't make a rule-based sort of MT system. But to explore syntactic relationships, we use Haitian instead of English for transfer, because Haitian and Jamaican have close syntactic relationships. And for orthography, instead of like an orthographic-based, rule-based engine, we just code switched or swapped in English words using a 200-word hand-curated lexicon. And for the phonological shared space, we did the exact same thing. Unfortunately, you might notice that this loses the phone order and the phone to feature mappings, which I'll touch more on later. These strategies helped slightly for Haitian. So the second row here is getting transfer knowledge from French, but without those two sort of additional linguistic transfer methods. And the score increases by about 2 blue points. Then when applying the orthographic engine, we got a slight improvement, which is statistically significant, but still not very large. For Jamaican, we got larger improvements by using the Haitian augmentation here, which is what we call syntactic transfer. And using the code switching, we actually got some improvements as well. But this also wasn't super satisfying to me just because these scores are still really low. We're still not reaching usable machine translation. Like just because it went from terrible to bad is not super encouraging. So how do we do this right is a big question. How do we get this phonological, syntactic, and orthographic transfer? Let's look specifically at phonological relations. So remember this is the method we were using before. It loses the order of the phones. So sur and russe will have the same exact embedding. These are the words for on and Russia, obviously not related. But even like bouffer and pouvez, which mean eat and can, those are going to have the same embedding as well, because the voicedness feature just moves over from the B to the V in this case, or the B to the F. This is what happens when we sum the embeddings. So some researchers and I had a quest to find fixed length embeddings for phone sequences of variable lengths that doesn't involve this sort of bag of words just summing it all together. So what we wanted was something like what's illustrated here, where the embeddings for ocean and motion will be close together and far apart from the embedding for soybean, even though soybean and ocean have similar spellings. And so we tried n-gram-based summation, as proposed by Chowdhury et al., padding with zeros and noise. This failed for Haitian, Lao, and Jamaican. So then we turned to using panphon feature edit distance. So when we convert the IPA characters into these feature vectors, we can measure their distance from each other. B and P are closer together because they're only off by one voicedness feature than like B and Q, which is the uvular plosive would be. Okay, so for various NLP tasks, we used count-based embeddings, autoencoder embeddings, an LSTM with metric loss, and an LSTM with triplet loss. What I mean by metric loss is that we trained an LSTM with the objective of making embeddings that preserve these panphon edit distances between words. And the triplet loss was essentially just, it's a contrastive loss. So basically, we wanted the distance between ocean and motion to be less than the distance between ocean and a random word, like soybean. And we found that the count-based vectors were actually best on cognate detection, but that the LSTM triplet loss was best on most other tasks. Sound analogies, rhyme detection, faithful representing of articulatory feature distance as well. Unfortunately, we didn't make any breakthroughs for machine translation. So this is still something that is, the jury's still out for this one. So if you're thinking, what should I work on for my next project? Maybe you could explore some of these ideas. One idea we had was to phonologically embed words just as TTS representations. If you think about it, a TTS spectrogram is sort of a phonological embedding. Or new ways to incorporate phonological embeddings into MT. We were just initializing the embeddings with the phonological information, which might just get kind of erased when you sort of train it on the whole MT task and everything. Let's look at phylogenetic relations. So remember, I showed these trees earlier. On the left are Sinitic languages, descended from Proto-Chinese, and on the right are Romance languages. And so this can inform linguistic transfer in that close languages may be better candidates for cross-lingual transfer. For example, if you're trying to train a system on Hakka Chinese, then Yue Chinese or Cantonese might be a better bet than Northern Mandarin. Or on the right, if you're training a Galician system, you should probably use Spanish or Portuguese before you would use Romanian. But they can also help in sort of a more fine-grained way, which is the reality that each branch in these trees represents a group of shared sound changes. So the Western Romance languages have a set of shared sound changes from Proto-Romance, and then the Ibero-Romance languages have a slightly larger set of shared sound changes. And so if we could train a model to predict these sound changes, that has interesting implications. An example is where we have the D sound goes to a J when it's before the R, from basically 18th century English to Jamaican patois. So like the word dream became dream. Anyway, if we could train a model to predict these sound changes, it could make an actually potentially functional version of what I tried to do in my undergrad, which was this rule-based system of trying to transform, French words to look like Haitian words. I was just doing it from my mind, but a model that could predict these patterns could potentially do something like this a lot better. So some steps forward in this vein, some colleagues and I at CMU developed an engine to extract shared sound changes based on work by Colin Wilson here at JHU, where we induce rules, given words, we align them using the same feature edit distance that I described earlier, which ensures that vowels will be aligned with each other. This post pharyngealized T will be aligned with a normal T instead of some other letter. And then this alignment actually gives us a highly specific rule where we see the pharyngealized T goes to a normal T in this specific context. And this algorithm actually comes with a generalization process so that these highly specific rules will get generalized the more data that we put into it. And we also trained a neural network to predict intermediate sound changes. So this neural network is trained on a lot of actually observed sound changes from the Index Diachronica, which is this linguistic database, has a lot of sound changes in it, to predict sort of which features in a sound are most likely to change when a language is changing into a new one. And so this predicts these linguistically plausible paths where if we see a yod going to an S, it may have become an esh in between, or a P to a W may have gone from P to F to V to a bilabial or labiodental approximant before becoming a W. So we call this first task automatic sound law induction because we're getting these sound laws. And the second task is called automatic intermediate sound change prediction. And using these two tasks, we actually predicted a phylogeny. So the two Kanoan languages are hypothesized to have descended in this pattern. And we were able to predict, while automating a lot of these processes that were done by linguistic experts, a very similar phylogeny. Another potential routes to sort of go about this problem is automatic sound law induction with LLMs. So because sound change is regular, for instance, like a D goes to a J when it's before an R, it can be represented as Python code. And so this is the brainchild of my former advisor, David Mortensen. But the idea is we explain to an LLM, you would like to implement this basic action object, which essentially changes the words in this language to words in this other language. And then we give it a bunch of examples and the LLM can kind of predict what the functions of that object would be, which we are representing as the sound changes. So a group of colleagues and I, we call this PySlick coder. I don't even know if I'm pronouncing that right, but we fine-tune magic coder basically with synthetic data. And we've actually found that we can outperform other open source LLMs. We're still not doing as well as GPT-4, but doing better than a lot of these code LLMs, llama variants with our PySlick coder ensemble method, as well as traditional methods. So on the right table, the top row is Luo et al.'s approach, which doesn't use LLMs. And we're doing better than it in some settings, but still running some experiments here. So other potential areas of future research include, yeah, go ahead.
So it's kind of interesting and maybe a little scary that the LLM is able to, come up with theories explaining, I guess, not large data sets in this case, like how much did you feed into the prompt?
Pretty small. Yeah. So in terms of synthetic data, we created 500 synthetic languages, each having like 5 sound change rules and applied to like I don't remember the specifics, but it was like 200 words or something. So it's like a few tens of thousands of examples.
Tens of thousands of examples.
Yeah. No, not in
That
one
was the
prompt.
total of all examples overall.
That's the total of all examples that we're sampling from.
Yeah, what I'm
Yeah.
asking is, if I ask an LLM, I say, here's all my astronomical data, find the physical laws. It's probably not going to do it.
I don't think it's going to do at all.
But if I
No.
ask it, here's 10 examples, make some proposals. Maybe it'll at least make good proposals. Maybe even the highest probability proposal will be right.
Right.
But I'm trying to get a sense of how well it does on problems like this.
Right. So when I say tens of thousands of examples, that's over all the languages. So we have like 500 languages with like maybe 100 sentences each, and each one of those is kind of its own thing, right? We have one language pair, and we want the LLM to predict the sound changes in that language pair. So we give it like 100 examples.
So it's 100 examples in one problem.
I believe so. They may have changed how they were doing it. So I was mostly involved with the synthetic data creation. But it's thereabouts, like it's on the order of a few dozen examples, basically.
A few dozen, okay.
Yeah.
And then do you trust what the LLM says, or do you say, we're going to use it as a proposal distribution? And say, run it 10 times to get 10 different hypotheses, and then evaluate those according to some ordinary metric that says, how well does it explain the data?
Right. So we were just seeing if the rules that the LLM generates are harmonious with all of the data that we have. And that's what the GPT-4 was able to produce rules that were completely harmonious with all the data. Now, we don't know if that's actually comprehensive because a small amount of data isn't going to comprehensively represent how a language changed over time.
Right. Also, to say that they're completely harmonious, that's emphasizing precision rather than recall. Is that right? You want to make sure you didn't get any bad rules, but you might not have gotten all the rules you need to explain the data.
I believe it's emphasizing both because you need to explain all of the changes that happen in the data that we have. So it has to be precise as well as have all the recall. Yeah.
What you mean by, I didn't know how you
yeah.
meant by harmonious, I guess.
Yeah, that's a good question. Let's see. So basically you have all these changes and the LLM is trying to predict these sound changes, and we want to see if it both covers all of the changes that are in the data and if there are no like extra rules, essentially, right? I actually think it's prioritizing recall over precision here because we're more interested in if the LLM is actually reproducing all of the changes that we see in the small data set that we gave it. Yeah. But anyway, did you have more questions or?
I always have more questions.
Okay, let's go on. Let's go on. Okay, so let's talk about structural relations now. So I mentioned that Haitian is syntactically related to African languages. This is in part because of the history of African diaspora Creole languages. And so these languages were sort of came about during the colonial era when African slaves were forcibly removed to the Americas. And they spoke lots of different languages, not the same languages as each other. And so new languages emerged in their communities. And these new languages were heavily influenced by the European languages of the slavers. And so this deals with the Creole hypothesis, which is that languages like Haitian and Jamaican have syntactic relationships with African languages, but lexical relationships with languages like English and French. And so one question that we wanted to explore here was, which group of languages is actually better for cross-lingual transfer if we use African languages or these European languages? And so, we gathered a group, Haitian, Jamaican, as well as a group of West African languages that could be their ancestors, and French and English, and we ran these comparisons. So essentially the question was, Haitian plus French or Igbo or Fanti or Twi to English translation, is that going to be, which one of those transfer languages is going to be best? And then the analogous thing for Jamaican. And we did this by, we had this multi-aligned set where the French, Igbo, Fanti, and Twi sentences are all exactly the same. So we're not getting any extra benefit from the fact that French has a lot more data online. We're just comparing purely linguistically, which is theoretically more helpful. And anyway, so we had an even playing field, and we added each of these to the training data successively. And for Haitian, the best transfer language was actually Igbo. And for Jamaican, we found that English and Igbo were the two best. When we allow all of the data to be used, This is maybe not quite a totally fair comparison with French because of the training method we were used, it probably just overfit on the large amount of French data. But Fonte actually works a bit better than Igbo for Haitian. And then we saw the same languages working well for Jamaican. A major limitation here, though, is that we only used 2 Creole languages and 3 African languages. And so we could get potentially more interesting results if we expanded this to a larger pool of languages. There are actually a lot of Creole languages in the world, and they're quite diverse. We have some that are spoken by millions of people, like Niger and Haitian Creole, and some that are spoken by a lot fewer people, like Jamaican Patois, Papiamentu, and Louisiana Creole. This map shows different Creole languages throughout the world that are color-coded according to which European language or which colonizer language they are related to. And here we focus particularly on this Creole civilizational region, which is like the Caribbean area. These languages actually have a shared linguistic history, as I talked about before, and because of that, they are related to a lot of African Creole languages, which we also included in this study for linguistic cohesion. I already touched on a lot of the benefits of LRL MT. These also apply to Creole language MT. You might have noticed I was talking about Creole languages a lot anyway, but for any of these benefits to be possible, we need data. And that was sort of the main limiting factor in that preliminary study, which is why we had so few languages. Even really multilingual MT systems only support a few Creole languages. So like 8, 5, and 8 for these big, massively multilingual MT systems. In recent years, there have been some works on machine translation for Creole languages, for Haitian, Singlish, Niger, Jamaican, Martinican, and Sranan-Tongo, and a few works on other NLP topics for Creole languages, on Singlish, Niger, Jamaican, Martinican, but not very comprehensive. Last year, there was another work that was really similar to our own called Creole Val, where they released an MT data set for 28 Creole languages, but they were all Bible and religious text, and there was no public release of the data. And so we tried to address these limitations by making the largest and most diverse MT data sets for 41 Creole languages, and the first ever for 21. We released a public data set with 11.6 million aligned sentences and 3.4 million monolingual sentences for 40 of these languages. This is some of the genre breakdown. So instead of just having 2 genres, we actually had 8 genres represented throughout the data set. And we released public models achieving state-of-the-art on a public benchmark that existed for 26 of 32 translation options that were actually supported. These are the largest ever data sets because we conglomerated previous works and because we added 410,000 lines of novel bytext through gathering and extraction of just data sets online that had never been converted to machine translation bytext before. This was done with 17 researchers. We had one L1 Martinican speaker and various L2 speakers of Haitian, Guadeloupean, Louisiana Creole, Niger, and Ghanaian Pidgin. These are the languages that we covered, both in the Caribbean and in Africa. Let's see. So it was about 24 countries and territories in the Caribbean were represented, as well as 16 different countries and territories in Africa. And I pointed out that these languages, this is sort of a linguistically cohesive group because of their shared history. So for instance, Nduka and Saramaccan of Suriname has been hypothesized to be related to Creole of Sierra Leone. Papiamentu of the ABC Islands and Cabo Verdeano of Cape Verde are often considered to have a shared ancestor. And there are shared linguistic traits that have long been noted by linguists between Louisiana Creole and the Creole languages of the Indian Ocean in the Seychelles, Mauritius, and Reunion. We also noted in our experiments that there seem to be indications of cross-lingual transfer. So for example, Mosquito Coast Creole, to English translation, we achieved 43.7 blue and 60.4 CAREF score with only 391 total bytext. And Vincentian Creole was even better with 55.5 blue, only using 321 total bytext. And so just for reference, there is absolutely no way that only using that small amount of Mosquito Coast Creole and English bytext without any other data from other Creole languages that we would be able to get a score that high. It's likely because, well, probably because of a few things. First of all, just having a big data set like that, we have a lot more English data, some of which is in a related genre to this Mosquito Coast Creole bytext. But also, Mosquito Coast Creole is very closely related to other Creole languages like Jamaican Patois and Bahamian Creole, which were more well represented in our data set. And so likely it's benefiting from some kind of transfer as well. We actually beat the Creole vowel model on their own test set by an average of 0.64 CAREF into English and 14.1 CAREF into Creole. And we scored the best on 26 of the benchmarks. Let's see. So potential ways to sort of build from this work are to build state-of-the-art Creole MT systems, either by fine-tuning the model that we used or augmenting the data set that we used. And I've been doing some sort of joy project stuff with this too that I can talk about later if anyone has questions. You could also develop language models for Creole spell check. So a lot of Creole speaking communities, they don't have the kinds of tools and resources that we take for granted, like spell check. This is a large amount of data that could train something like that. This is text data that could be availed for speech applications in some settings. It could be used to study cross-lingual transfer phenomena. So just because of the well-studied relationships between these languages, in some cases well-studied, this is something that could be looked into, or develop tools for endangered language documentation like Louisiana Creole. We'll touch a little bit, okay, we're running a little short on time, but we'll touch a bit on acoustic relations as well, because this is an interesting field of research. So a lot of low resource languages really need ASR because of their oral traditions. They might be endangered or just, to develop the tools that we English speakers often take for granted, like smart devices. Even the most widely spoken African language, Swahili, which is debatable, some people would call it Hausa, but anyway, Swahili is one of the most widely spoken African languages, and it doesn't have a high quality ASR system, or at least it didn't when we did this study. So some colleagues and I endeavored to improve ASR for Kiswahili, also known as Swahili, Guarani, and Suba, which are languages of Kenya and Paraguay. These lack large labeled speech data sets. And so our approach was, what if we can use text-to-speech, or TTS, to generate training data that we could just throw into an ASR system? The problem is, like I mentioned, these languages don't have data sets, so they also don't have high-quality TTS systems. And so our strategy was, we want Swahili speech with a transcription, and what we have is just Swahili text. So what if we used Microsoft Arabic TTS? We just put the Swahili text in there, and it'll give us some sort of like noisy sounding Swahili. Henry's really wincing back there at this idea. It gives us accented Swahili speech. And so in this case, we call Arabic the pivot language, and we have the transcription and the speech. So the transcription is just there, and this is data ready to go for ASR training. And this is inspired in part by Microsoft's statement on their website, where they said all neural voices are multilingual and fluent in their own language and English. For example, if you input text in English, I'm excited to try text-to-speech, and you set Spanish, then the text spoken is going to be in English with a Spanish accent. Granted, we're kind of expanding on this assumption and applying it to things that are not English. But the idea is that it'll output accented speech. Yeah, go ahead.
Why the Arabic model?
We did a few different languages. This is just an example.
Oh.
Yeah, so this is a question. Which pivot language to use? Arabic or something else? So for Guarani, basically we selected languages by looking at a few things. If you've heard of Uriel Langtevek, it has different like distances between languages in terms of different dimensions. So Afrikaans had a high phone inventory with Guarani. Yeah, I guess the key is down here. So if they're phonologically close, we use this cross symbol. If they're phylogenetically close, like they're related, then we have the double star. And if they're geographically close, we use this single star. And then we also had some random languages, just as like controls. So, and then the bolded one is the best performing. So we actually found that we couldn't find any clear predictive language relationships. So for Guarani, the best pivot language was French, which was just the random language that we decided to put in there. For Swahili, it was Arabic, which is geographically close. But otherwise, like, it's not entirely clear why that would be best. And then for Italian, Spanish and Finnish both did better than Romanian, which is very phylogenetically close, even though Finnish was just the random language that we threw in there once again. And so one question that we have is it even better for them to be closely related, or maybe distant languages are even better because it's giving sort of extra diversity, which might help the model be robust to noise. Who knows? Whoopsies. So these are some of our results when we used the these are word error rates and character error rates, which were greatly reduced, but still bad. This is kind of a common story in low resource language technologies is you'll reduce the error rates a lot, but they're still not very good. Interestingly, to Matt's question, the Arabic TTS, when it outputs the Swahili, I guess we used two different systems. We used a Google system, which was not as high quality, and the output sounded pretty bad. Like it's hallucinating all these Arabic characters that weren't in the Latin script text and everything. We did another sort of strategy where we actually transliterated the text first and then put it through the Microsoft system, and it sounded way better. But it was not any better for this application. So even the bad sounding speech was just as effective as the better sounding speech, which was basically this study kind of introduced more questions than it answered. So one thing that I've been interested in doing, or that any of you could potentially try, is to expand this study to more languages to find patterns. We couldn't really find any patterns due to the fact we were only looking at 3 languages with a few transfer languages each. But with a more comprehensive study, maybe some patterns could be found. Yeah, I mean, this is pretty much what we have for this study. So there's not much of a pattern here. Um,
Although it's geographically based on the language geographically close versus genetically or phonologically, what was the conclusion?
right. Basically, it was more of a non-conclusion because we didn't really find a pattern. So as you can see, like Arabic, which was geographically close, helped a lot for Swahili. Unfortunately for Swahili, there were no phylogenetic relations that Microsoft TTS even supports at the time that we did this. So we couldn't compare for Swahili with those other ones. Guarani, we compared this phonologically close, geographically close, and neither of those did best. And then with Italian, the phylogenetically close one also didn't perform best. So
Same words, same meaning, sounds very close to each other.
no, not the same meaning. It just means that if you take the set of phones that exist in that language and you take the overlap with the set of phones in the other language, it's going to be large. So like Afrikaans and Guarani aren't related in any way, shape, or form, but if you just take their set of phones, they have like a high overlap. Synthetically close? Syntactically. Yeah, that's not one that we explored here. But that could be one that could be explored. Yeah, this is something that I would like to see done in greater depth, definitely. If not by me, then by someone, but I might do it at some point too. Okay, so this can also be applied to accented English. The idea is you take English text and put it through a Spanish TTS model, just like Microsoft promised. It's accented English speech with as if like a native Spanish speaker were speaking. And so we actually used this to try and make English ASR systems more robust to people with different accents. Since this is a problem that lots of people in the world face, they have an accent, Siri can't understand them. This didn't really work. It only improved results slightly for 3 out of the 9 accents evaluated. Yeah, so, and this is partly because we had scarce, undiverse data. We were evaluating on these data sets that there was so much overlap between the train and test sets that we really had to trim down the train sets to almost nothing. And the also just kind of a problem throughout this work is that TTS audio is just fundamentally different from human speech. And it's really hard to get on par with like human speech training data if you're only using this synthetic, or you're using a lot of this synthetic data. And so one thing that Bismarck tried with some help for me and other people was synthetic data for Spanish to English speech translation. So he also found that this sort of type of augmentation helps a lot in the speech translation setting between these high resource languages. So it was successful, and that basically using more data is just always better. If you use more real data, that's better. But then if you're able to pad it with more synthetic data, it also improves the performance. However, this was only effective with the presence of at least some authentic data. And well, essentially, I guess I neglected to mention that they used voice conversion to bridge the gap between TTS and authentic speech. So basically making the synthetic speech, we used a voice conversion model to convert the voices to match the training set of the actual real speech voices. So we were just trying to copy the voices in the actual authentic speech. But the problem here is that voice converted speech is still synthetic. And so there still might be difference that would be imperceptible to our ears or maybe even perceptible, but that could be significant. And so another potential area of research is to overcome this difference between text-to-speech and human speech differences, maybe by doing voice conversion at inference. So that was something Bismarck and I wanted to try at some point, was essentially you could intentionally overfit a model on a synthetic voice, but then at inference time, you just convert any input voice into that one voice that the model knows how to do. And theoretically, that could maybe overcome this issue, maybe using GANs. So I've wondered about, text-to-speech systems are trained to sound good to human ears, but what if they were trained to be effective for ASR augmentation? And that could be done potentially with sort of a multi-objective GAN or something similar. Okay, so wow, it's one. But if anyone has any questions, we can do that real quickly. And I guess you ask questions throughout as well, so no worries if not. Yeah.
So I like the sort of IPA phonetic approach. It's a bit like what Liz was doing with the visual representations.
Yes, not quite as technical, but yeah.
Well, yeah, but same in spirit, I think.
Same in spirit. Yeah, and the fact that we change things to feature vectors, so changing things to IPA is really nice because that way you overcome orthographic differences between languages, but you're still running into the problem if you just keep them as characters that there's no way to tell that a T and D are closer together than a T and a Q or something.
But presumably with enough data, it could learn that.
Yeah, potentially.
I'm curious too, if you did that in a multimodal setting, do you think you could, were you actually feeding it audio, just pre-trained audio without transcriptions, or maybe with transcriptions as well? I wonder if what you're doing is at all redundant in what's being learned. Do you think you could sort of similarly triangulate, not just with IPA, but with spoken audio in all languages? I don't know if you have any intuitions here or knowledge from stuff you've read, and maybe it take a certain level of scaling to get here with that. But I'm just curious to.
Right. So you're saying, what if we essentially sort of, it sounds kind of like, so my one friend told me to just use TTS as a phonological embedding. That's just speech. But maybe you could find some sort of embedding that's actually induced by natural speech, by human speech. But also include the IPA. Yeah, I think there'd probably be a way to do that. It sounds.
I mean, you could do a bunch of things. You could train a big multilingual system, many to one, like many to English, for example, and just convert all of the input to IPA. I wonder what kind of gains you get there, for example.
Right.
But then you could also try to give it audio of the different languages that are on the input in hopes maybe that something you're learning about the audio could help it establish a correspondence with the IPA, and then the IPA together, so you can kind of complete the size of, I don't know, whatever shape this is.
Right. I wonder.
I'm just kind of speculating, so I don't know if you thought about this at all.
Yeah, we did do some experiments in my master's where we just converted everything to IPA. So we had a Haitian data set and a French data set. Convert to IPA, suddenly there are more sort of overlap between the tokens. And it improved results slightly, but not that much. I am wondering maybe what if we had tried with a model like Seamless that actually does speech and like text MT, so it has speech representations as well in the model.
Yeah,
I
exactly.
wonder if that would help for it to like catch on to some of those phonological relationships more. That would definitely be an interesting direction of inquiry. Yeah,
I just want to have kind of an off the wall question. You might
sure.
not be the only person here who has something to say about it. But it's interesting that a lot of this kind of engineering, which we used to do throughout NLP, has fallen away, but it still seems to be necessary here. So, there's sort of a lot of big transformers are the universal solvent, and you just feed them the right kind of data,
Right.
and they pick up the generalizations they need. So nobody seems to be worrying much about misspellings. If you type in a misspelled query into a chatbot, it just like sees right through it.
It should be robust to that
In
noise.
fact, it actually knows a lot about spelling and pronunciation.
Right.
Already, and you can demonstrate this by various things. So it's
Right.
interesting that it seems to be necessary here, and not,
Mhm.
we're not dealing with low resource spellings, low resource topics, low
Sure.
resource registers. Like different kinds of style. So I wonder whether we should be using these methods for those other problems and we do even better, or if these methods are only temporary and there's some way, either in probably in the training data, the transformer, but possibly in the architecture, that would allow us to not need the special methods anymore.
You're talking about these spelling differences?
Yeah, I'm talking about sure, these spelling differences, the use of bridge languages,
Right.
Including like the French prime that you prepared, which is
Right.
partially translated into Haitian.
I think the real root of the issue there is that like if you're misspelling things in English with an LLM, it's seen so many of those examples, even of those misspellings, like so many more examples of just English misspellings than it has seen of Haitian Creole sentences most of the time. Or take an even lower resource Creole language, and that's certainly true. And so it just doesn't have the data to pick up on those kinds of spelling variations as well. And so this is kind of an effort to get around that fact. Because either we just have to make tons more data, but that's an expensive process.
Well, it could be tons more built data, but maybe synthetic data is cheaper.
Yeah, sure. Okay, so you're saying that one possible way to do this is actually something Nia T and I are sort of doing right now, which is just like create synthetic data with lots of random misspellings and see if that'll help the LLM be more robust to real spelling variations, right? Is that kind of
Sure. I mean, there's a number of things you could do. You could also do it at the type level where you say, okay, here's some dictionary, and try to generalize the spelling rules as you were saying before.
sure,
And okay, now what do you think compound means
right?
in this context?
When you say a
Like,
dictionary, you mean like
if you have that as an intermediate test. I mean, again, that's special handling. So I'm not saying that this is bad. Like it's probably the kind of engineering that we need to do at this point. And
Right.
I'm wondering if it's a temporary phase in the development of NLP, since a lot of things that are like it seem to have faded into the background.
right. So when you say like a dictionary, like a bilingual lexicon, and it could sort of learn those spelling relationships. Yeah, I think that's a great idea too. This is something David sort of recommended to me at one point too, which is what if you just trained a model to convert from one spelling system to another, and then you could create a lot of synthetic data from a model that knows how to do that. Yeah.
I mean, you would hope eventually you would have a system which is like able to roll with punches and
Right.
give it funny spelling. I don't know. Yeah, I don't know. If you look at Pygmalion, George Bernard Shaw tries to write out what the cognate, I think, dialect sounds like.
Sure.
And he does that for the first several lines and then he shifts away from it. So you could kind of puzzle it out.
Potentially.
As a reader, especially if you've heard that dialect before, you would hope that maybe the LLM is able to like puzzle out things it's never seen before.
Right. The question is whether it can do that in domains where it really just hasn't seen that much of that kind of data. And potentially maybe LLMs could be adapted to that sort of thing with relatively few data. I think that's still being studied, but I think these are low resource. Like by definition, that's what we're focusing on here. That's what I'm focusing at least on is low resource languages. So how do we solve some of these issues without having tons of data available?
I don't know if anybody else has a.
Yeah, I mean, it's 1:10 already, so yeah.
Oh, you might take it. But like, my view is one of the business strategy in across languages. As long as there are specific techniques to take advantage of large quantities of data, then techniques or specific engineering, as you described it, that augment the availability of data is always useful. So in a way, yes, it's almost temporary, but it's also constant temporary. Like
But if it is temporary, it's not obvious to me how it'll go away.
Sorry, I didn't catch the last.
I said if it is only a temporary phase, it's not clear to me what will sweep it away. Like, what is the thing that will make it unnecessary to do this kind of engineering? Is there something that's waiting for us?
Yeah.
That will fix it. Like we wouldn't have been able to say 5 years ago that large transformer language models would sweep these other things away. So we may not be able to see it coming.